Okay, let's see what we have. All right, for your slides on the lecture side, that one has been updated. So we're going to start talking about the first refinements of the bridge controller today. So make sure you go to the same link, and by that one there, make sure you refresh your browser, and make sure you download the latest slides. That one should cover all the way until the end of the first refinement I'll show to you. Just make sure you go to the same link over here. It was just updated today. Right, click on that, re-download it, or reload to your tablets if you want to take notes. And I released yesterday your lab number 2 solution video in case you're still struggling understanding the relational operations for your lab number 2 solution, especially like an inverse, relational image, etc. How can you find it? Again, on the lecture site, you can see right underneath the programming test 1 guide, you can see lab number 2 solution walkthrough. The video and the notes, you can find both. Right? If you want to have any follow-up discussion, let me know. I do have office hours as usual today. And for your practice number 1 solution, if you go to the E-class over here, you will see under programming tests over here, you got a solution. PDF as usual. If you haven't really tried to really look into the informal document for practice test 2 and formulate it in Rodin, I would suggest you do that first before you look at the solution. That's what you will have to do on Thursday during the lab test, right? It will be a very nice practice for you. Take a look, and not too sure if we may have time today to really go over any highlights about the solution for your practice test 1. I'll see what I can do if I can at least have 5 minutes even just to highlight anything. But again, go over the solution and come to me. You still have the office hour today and for tomorrow. But most likely the office hour for tomorrow will be over Zoom. But you can just dial in and then we can talk. All right, you still have time to get prepared for your programming test 1. And the last item, which is also very important, is not so urgent for your upcoming written test or the programming test. However, it will be important for your final exam. Okay? So I already explained the math, back in the announcement I made earlier today. Basically, for all the missing time from these 4 tests over here, since we take the normal scheduled time for the classes. So to really make up the time for you, I'm thinking that rather than just showing maybe bits by bits of the bridge controller, which can be interrupting, for our lecture pace, let me only focus on the bridge controller in the in-person classes like today. And for all the missing time here, I would say it should be sufficient just for now. In case I need to add anything extra, which is unlikely, but if I do, I'll let you know. But this is where you have to study before the final exam. Let me show to you where you can find them. It's already there. You can definitely start from today. And you got more than a month before the exam occurs. So you do have enough time to go over them. Again, the lecture site, you will see there's one row over here about makeup lectures for all your tests, right? It's already self-contained, the lecture. So you got different parts of the video, and then you got the notes, you got some proof, and etc. Also the slides over here. I think at least you will be able to understand the very good part of it, because that one there hasn't really talked about refinements. But as we talk about refinement idea in the bridge controller in class, you will also be able to understand the second part of the lecture. But it wouldn't hurt to actually start with this, right? Again, this will not be covered in any of the written tests or programming tests before the end of the semester. But this lecture here will be covered in the final exam. All right? So, but your best interest should be study that steadily and reach out for questions if you have any. Yes? Yes, absolutely. Yeah. So, I'll give you guys a little bit of motivation. While you guys are still it's kind of fresh in your mind about the mathematical review, right? Relations, functions, etc. For the bridge controller, we don't really have to use any of the relational functions. Not really. We only stay with the natural number. However, for this case study here, which is about modeling some file transfer protocol, we actually do use relation and functions. And that's a very nice case study to see how things can be modeled formally using functions and sets. Right, so that's something I really want you to study carefully. Right? I think, again, the lecture is very self-contained. You can definitely start even from today. Right? You should have no trouble following the very first part without any refinement. Okay? All right, guys, do you have any questions for now? Anything that's unclear to you? How are we going to run the course? Well, we got about 5 weeks left, but we still got a lot to learn, which is good. All right? Anything you want me to know? I already read through your midterm survey. I really appreciate your feedback, but something I can do, something I may not be able to do this time, but I'll try my best. Okay. Any questions? Awesome. Okay. Let's now start with the first refinements for the bridge controller, and then if we have time, we'll talk a little bit about your practice test 1 solution. Okay, that one shouldn't be too bad. Should be quite straightforward. Okay, so let's now see what we got from last time. This will be a very nice summary about what we did in all the past weeks about bridge controller. Okay, very quickly. So let me just go over some bullet points. So we kind of show that our final version of the initial model M0 without any refinements is provably correct. You got to be very careful whenever you declare some model is provably correct. The follow-up question should be, what kind of criteria did you use to prove it being correct? So there are several criteria we used. Number 1, about establishing the invariance. Number 2, about maintaining the invariance between the event occurrences. And the final one would be about deadlock freedom. Because it's a reactive system, you definitely don't really want your system to stop reacting to the outside world. So it's got to be deadlock free. So these are the 3 criteria that we actually prove. And so this another important part of this course is to say, given this initial but very simple model, is it possible to introduce some complication or some more details to it, so we can cover more aspects of the requirements documents. So far, we only cover a single requirements in the requirements document, and we would like to cover more in the subsequent refinement model. So that'll be the plan. And just remember, whenever you introduce some further details in the refinements, you are still subject to invariant establishment, invariant preservation, and deadlock freedom. And there will be a 4th criterion. Let me give you a little bit of a look ahead. You want to somehow prove that the refinements is indeed a mathematical refinements. So there are some certain associated rules you have to prove. But we'll discuss them very carefully later. Not for today, but later. All right, for the initial model, we have a summary over here. And you got the constant, axiom, variables, and etc. Right? So you don't really want to abandon your memory about this model here, because when we talk about M1, very often we have to draw a connection between the so-called concrete states in the refinements to the corresponding abstract states in the initial model. That's something we'll see. All right? That's about what we have covered in the past weeks. And what we want to do now is to introduce something that's more concrete. Right? Remember, part of the title of this course is about refinements of system. There we go. All right? So in the coming weeks, we're definitely going to talk about, hopefully, 2 subsequent refinements. Refinement number 1 and refinement number 2, one by one. Okay. All right, let's now go over some bullet points, and then we have to visualize what the difference is between the first refinements and the very initial model. Okay. And the first refinement has a more concrete perception of the bridge controller. Okay. If you just recall very quickly, let me show you the diagram. This one here is the conceptual understanding of the initial model. We kind of don't distinguish between the island and the bridge. We kind of consider them as one single compound. And you can imagine that you're trying to perceive the system from very high on the sky. So now let's lower our latitude a little bit so we can see the system a little bit more carefully. In that case, we're going to see a split of this compound between 2 parts. One would be still the island. The other part will be the actual bridge. So this is the concreteness we're going to introduce to the first refinement. Okay, let's see. All right, so we're going to zoom in to actually see the system a little bit more in more detail. So in that way, we're going to see the bridge. Okay, so we're going to see the island, and we're going to see the one-way bridge. How should the diagram look like? So this is the diagram you should now remember for the discussion for refinement number 1. This will be the diagram. Let's take a look. Okay. Again, this is the initial one, which you're very familiar with. This is the final one. Oh, sorry, this first refinement. Okay. Now, what you really want to do today, maybe after the class, I'll help you a little bit. You want to think about what's really the connection between 2 diagrams. Nothing about right or wrong. They are describing the same system, but one is more abstract. The other one is more concrete by introducing a little bit more detail. Okay, let's see over here. If I look at this diagram over here, okay, you have island here, you have the breach over here. They are being made separate notions. And also you have the mainland over here as well. And then you remember ML out and ML in, right? Now we have introduced also two events that's new. There may be a car going from the breach into the island. That's going to be denoted by ILN events. You may have one car that's going to leave from the island onto the breach so they can go back to the mainland. That one is going to be denoted by IL out. So ML stands for mainland. IL over here stands for island. Okay? Let's try to see how we can perceive the initial model from this picture. We really want to see overlaid effect. So let me use the green to represent the initial model. Okay. Think about when we didn't really distinguish between the island and the breach. Think about this part over here, and that will include ML out and also ML in. Initially, when we created M0, we didn't distinguish between this one and this one. They are considered as one. Okay? So the green one there is really the initial abstraction. The initial abstraction. No distinction between island and breach. That one is a reminder. And for the first refinement, we're going to do a split in the following way. We're going to say, okay, I'm going to take this part over here as one component in M1. I'm going to take this part over here as a second component for M1. Okay, this one, this one. So think about this one here and also this one here. So these are separate components in the more concrete first refinements. All right? And one very important thing to mention is a look ahead. We're going to see ML out and ML in. They kind of already exist back in the initial model, but they still exist in the new model here. So we have to see how we can somehow redefine or overwrite their definition. We're going to see that, depending on what variables we have in the initial, in the first refinement, of course. But we'll get there a little bit later. Okay, and then so these two, IL in and IL out. So these two events will be considered as the new events. Okay, so these two, one here and also one here. So these two are the new events. Two new events. Whereas ML out and ML in, they are the old events we call. And these are the two old events which already exist in the initial model. All right? Are we okay so far? This diagram here is really important. It doesn't really say too much, but on the other hand, it kind of clarifies about how we can overlay the two level of abstraction between M0 and M1. Okay? Let me make a final remark, and then we can go a little bit deeper into the details. Both M0, which is over here, this is M0, and this guy here is M1. And M1 model the same system. Okay, that's point number one. And point number two, however, we say that M1 refines M0 by adding more state variables and events. We can already observe these are the two events we introduced in the refinement. We'll see some new variables that we have to worry about when we do the proofs as well later. All right, a final thing to mention. What are we addressing in this first refinements? We are trying to address these two requirements. If you go back to the very beginning of the slides, we talk about the requirements documents. So requirement number 1 and requirement number 3 are our focus for this first refinement. Let's take a look. The system is controlling cars on a bridge connecting the mainland and an island. So that's exactly the one-way bridge that we have to separate from the compound that exists in the initial model. Okay? And for requirement number 3, how do we address it in this in this first refinements? The bridge is one way or the other, either going from the mainland to the island, or it might go from the island to the mainland, but cannot be both. It's not a two-way bridge. Not both at the same time. Now, for requirement number 1, we can already see we got a bridge. What about requirement number 3? How exactly do we address this requirement here? The way to do it is by adding more variables. You can think about those variables are more like a sensor variables to somehow record how many cars are actually somewhere. So here we try to record 3 things. How many cars are actually in the island? How many cars are on the bridge heading to the island? How many cars are on the bridge heading to the mainland? So these are the 3 quantities that we have to maintain in the first refinement. Don't worry, I'm going to talk about a little more detail, but I just want to point to you. All right, again, to really address these requirements, we need variable number 1, recording from here to here. Variable number 2, recording from here to here. And variable number 3, recording what's really the number of cars in the island. All these quantities are important. We have to make sure we can use these variables to define our events in the first refinement properly. And number 2, we want to make sure the way we actually update these new variables would be somehow still consistent with how we deal with the variable in the abstract states, in the initial model. That's something we talk about more formally. Sarah, question? No, they are not. Okay, so you can think about IL in, IL out over here. So these are the events that might occur in the first refinements. So whenever an event occurs, for example, IL in, it might change some of the variables that I just mentioned. In the next page, you actually see what variables they are, that's new, and also what events they are, that's new. We'll talk about it. Yeah, yeah, we got both the events and also variables, 2 things. Yeah. All right, any question so far? Okay. Usually the introduction is not too bad. Just want to make sure I understand what exactly are we trying to address formally in these refinements. Okay? And when we get to the second refinements, possibly in the final 2 or 3 weeks of the semester, and then we're going to talk about what other requirements we want to address in addition to requirements 1 and 3. So that'll be the second refinements. We'll do that. All right, let's now take a look. Right, everything has been said, and we have to say we are obliged to really prove this added concreteness is consistent with M0. All right, just remember that. We're going to do that. So proving about invariant preservation, establishment, and de la freedom are pretty much the same as what we did earlier about the initial model. So we don't really have to spend too much time on that. I just show you the proof obligation. If we have time, we can do some part of the proof together in class. Otherwise, I can assign as exercise to you. We can focus more on the last bullet points over here. How do you prove? The first refinement there is formally a refinement of the initial model. There are very stringent rules that we have to follow. Okay, that's something we'll get to, possibly after your programming test number 1. Okay, for today, it's not going to be very heavy. Okay, so let's talk about state space. If you recall the notion about state space, that means the collection of the variables. All right, what variables do we want to have for this first refinements? Let's go over some bullet points on the slides, and then we can do some exercises together to try to formulate the invariants. That might be a nice way to also get prepared for your programming test 1. A very simple one. Okay, what will be the refined state space? Okay, so first of all, the static part about your model is the constant and the axiom. And these two, the static part for M1 will just be the same as M0. We don't make any changes. We can let them share. That's okay. Okay. Of course, in the rodent term, you can think about machine number 1 sees context 0. Machine number 2 also sees context 0. Okay. All right, just remember we got a D. Remember what that means. And also, we got axiom 1 and 2. And axiom 2 was due to some failed de la freedom proof from the initial model. Right? That's what we did last time. Just remember, we're using the fix. And what about the dynamic part? Dynamic part is what we're going to extend in the first refinements. We call this a concrete states. So the notion about abstract and concrete is really relative. Okay, I will just mention one page over here, and then we can. Okay. Usually, you have something called, let's say model 0 and model 1. Okay, it's relative. If I say formally speaking, if M1 refines M0, then we'll say M0 over here, all the variables, constants, they are called the abstract state space, just abstract states. On the other hand, the collection of the variables and the constants, they will be called the concrete states. And accordingly, not surprising, the events in M0, they are called the abstract events. We also sometimes have to call old events. I will try to make the distinction a little bit further, maybe next time. For today, that's okay. Just remember, sometimes we might say abstract events, sometimes we might say old events. Okay? Just for today, it's okay. You don't need to worry too much about the definition. And also we got over here, M1, we also got events. And we have to know about concrete events and also the notion about new events. Again, we'll only try to distinguish between these concepts maybe after your programming test 1 next week. Okay, we'll do that distinction. M0, M1. And when I say it's relative, later on, I will introduce another model over here called M2. Yeah, let me finish this and I'll take a question. If I introduce another refinement, let's say M2 formally refines M1, the principle will apply in the following way. That means relative to M1, M2 is more concrete. In that way, when we only talk about M1 and M2, in that way, we'll say the states in M1 is the abstract states, and the state in M2 is a concrete state. It's relative. There's no absolute abstract or absolute concrete. Okay, it's relative. Okay, so let me just make a notes over here. Relative to M2. States and events should be singular. States and events in M1 are abstract. But relative to M0, states and events in M1 are called concrete. Right? That's really the relative concept, depending on how which pair of the models you're talking about. All right, hopefully it's not too confusing. Right? Just some terminology. All right, so for the concrete states for M1, we're going to introduce 3 variables. And as I said before, for this bridge controller, we don't have to deal with mathematical objects. That's more complicated than just numbers. So only numbers. Okay? So we're going to have this idea over here. Okay? It's about a traffic flow I spoke about. We got 3 quantities over here to see the current state of the bridge controller. Right? We got A here, we got B here, we got C over here. Right? And these are definitions, but let me explain that. Okay, let me just see where they are. Okay, let's see, talk about this. Right? So this is just another, it's very more focused perspective of the first refinements. We got A here, we got B here, and we got C here. So we declare A, B, and C as the variables. Right? So that's a dynamic part of the first refinements, A, B, and C. And the first invariant, oh, one thing to note, you can see we got 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5, right? Remember the naming convention we spoke about before. Before, the invariant would have been, for the initial model, invariant 0, 1, 0, 2, 0, 3, and etc. But now, since we talked about M1, so they changed to 1. Okay? That's something just to make sure you don't get confused. So this part over here, that means we're talking about M1. Okay? And we talk about invariant 1, 2, 3, 4, 5. And we'll do these two as exercises together. All right? But before that, let's now clarify something that's more basic. We got A, B, and C over here. Right? So they are simply just natural number. Basically, cannot be negative. That's the only. If we have to add more constraint, we'll do that later. A, B, and C. Okay? And let's now annotate very quickly. A will be the number of cars on the bridge heading to the island. And by the way, this part over here is the mainland. This part here is the island, right? And this guy here is the bridge. Symmetrically, we also got C over here. So C over here will be the number of cars on the bridge heading to the mainland. And finally, we have B over here, the number of cars in the island. We got A, B, and C. You might have some confusion right away. You really want to keep thinking about what's really the corresponding concept in the initial model without this refinement. In the initial model, how many quantities did we use to really formulate the number of cards? Just one. Do you remember what it's called? D is the maximum limits. N. All right? So now you want to think to yourself right away. In the initial model, I only got one N. Oh, sorry. But now I got A, B, and C. As a requirement for the refinements, we have to make sure, as part of your invariance in the concrete model, you're obliged to really specify how these three concrete variables are related to the abstract variable. That's something we'll have to see. Right? I just want to mention to you. But we're going to do that very soon. Okay? Right? Make sure you understand A, B, and C, what they really mean. We're going to need them a lot, very badly, when we do the proofs later. Okay? And we'll get A, B, and C. And for the constant and the axiom, they're just the same. Okay? Let me see if I missed anything. And then we can do some very simple exercise. I can also clarify to you about what the answers for the exercise really mean. We got variables, we got invariants over here. So for the first three invariants, simply saying all the three quantities are natural number. And then number 4 and number 5, we'll do them together. And you want to understand some term, 1, 2, and 3, just about the typing, the types of the variable. So they are called typing invariants. These are rather straightforward. And these are the ones usually you can just drop using the monotonicity rule, right, in the proof. That's something we spoke about last week. And number 4 and number 5 is something that we have to specify together. Okay, let's do one by one. Let's do invariant number 4. Okay, for invariant number 4 over here, somehow we want to linking the abstract and concrete states, right? So at this point, you will be able to understand what I really meant by abstract states and concrete states. The concrete states is simply A, B, and C. Okay, so let me write it down. The concrete states is what we declare A, B, C over here. And the abstract states, let me see if I have the diagram handy somewhere. Let me see. Yep, it's here. If you recall, this is our initial model, right? And the only state variable we had was n. Okay, so let me go back. And that one there is simply just n. And we ought to have some predicates, some Boolean expression, which is going to link the relationship between n and also ABC. Guys, any thoughts about this? What should be the relationship? For example, one thing could be maybe n should be larger than or equal to a plus b minus c. I'm making that up. As long as it's a Boolean expression. Okay, go ahead. N should be equal to a plus b plus c. Yeah, that sounds very straightforward, but let's understand that. Okay, that's the right answer, thank you. But let's understand why. It's really important. Okay, for invariant number 4 over here, n should be equal to a plus b plus c. This part over here is the concrete states. And this part over here is the abstract states. And how do we see that? Not very tricky. If you remember what I did earlier, I tried to overlay the two models. Let's do the same thing. If you think about abstract states where we don't distinguish between the bridge and the island, in that case, what will be the n? It's going to include all the cars here, all the cars here, and all the cars over here, simply A, B, and C, right? Because in the initial model, the island bridge compound simply include this one here and also this one here. So that means whatever quantity you can observe from here, they are included in the calculation. So that's why, okay? Just remember, okay? And of course, in the concrete states, we actually got this guy here, which will be just B, and also this guy here, which will be A and B. Okay. Right, the first one. So what should you really study for the first one? Make sure you understand that this invariant here is a very special one. It's trying to link between the abstract states and the concrete states. We don't have many invariants like this, typically. Usually just one or two. Just to helps anybody read your model to understand how to link between the models. And then here, this is how you visualize it. Okay? Number 5 is very important. Okay? Let's say that's it. That's all you have. You say n is equal to a plus b plus c. And then you say a, b, c should be a natural number. Okay? Do you see any danger of the first refinements if we only have invariants 1, 2, 3, 4? Let me write out the question here. A very important one for you to think about. What's wrong if n1, the first refinement, is only constrained by invariance 1, 0 to, 1, 1. 1, 1 to invariance 1, 4. 4 only. What's wrong? Ryan, go ahead.
The bridge is a one-way. So if there's cars, if A is greater than 0, then C cannot.
Absolutely. You definitely get an essence of that. Very good. Thank you. Yeah, guys, what Ryan said was exactly right. If you remember, one of the requirements that we're trying to address over here, we said the bridge has got to be one way. Let me give you one counter example. Whenever you want to show, mathematically, whenever you want to show a problem of your model, you need a witness of the violation. Okay, let me show to you. So let me give you one witness. Let's say a witness over here. Okay, let's say A will be 2. B will be 1. B doesn't matter. Let me just A and C. That's really the important. C will be, let's say 1. And B will be, let's say 4. Doesn't really matter. Okay? So we got 2 here. We got 1 here. And then we got 4 over here. Right? Accordingly, n is equal to 2 plus 1 would be 7, right? As far as n is concerned, we don't see any problem. However, as you see more clearly about what A and C over here both being positive, so that means you got two cards moving this way. You got one card moving this way. What you get? Crash. It's violating some safety requirements for the breach being one way, right? So that means having only these four invariants is not sufficient logically to guarantee that your breach is safe. It's a very important takeaway message for this course. Whenever you're creating your model, having just typing constraint and also so-called linking invariants, linking the abstract and concrete state, they may not be sufficient. Most likely they're not sufficient. You have to make sure you also have any additional invariant that will guarantee safety property, right? Just make sure you understand that. All right, so what should we do for this one here? Well, it's going to be invariant 1,5. The breach is one way. How do we specify that? Okay, go ahead. A equal to 0 or equal to C equal to 0. Apparently, we want to make sure if we want the car to be moving this way, for example, in that way, this quantity over here must be equal to 0. Alternatively, if we want the cars to be moving this way, in that case, the quantity of A over here should be equal to 0. So we should really accommodate both scenarios. Okay, that's the intuition. So what you will have is over here. So you're going to get A equals 0 or C equals 0. So these are the two invariants you want to really make sure you understand before we resume next Tuesday. Okay. All right, guys, any question about what we have covered so far? Yeah, question. A? One implies? A, okay, let me write it down. Okay, so alternative for invariance 1,5. Okay, I'll put a question mark. Okay, say it again. A multiplied by C equals 0. Let me think logically. In that way, they both being 0 is okay, right? If one is positive, the other one is 0, that's also fine. Because if both are non-zero, it cannot be 0. Yes? That's a very good suggestion here. I would say, logically speaking, I agree. It's okay. However, this does not necessarily make it easier for you to do proof in the prover. Because here you're involving multiplication. In the case where you want to prove some sequence, you have to manipulate the multiplication in this way. On the other hand, if you got A equal to 0 or C equal to 0, that could be very beneficial, right? We do know some inference rule about dealing with disjunction. We also know about the EQLR or EQRL. That might also allow you to do some substitution. So I would say, even though they are logically equivalent, but this might be more favored by you because you can manipulate the proof more easily. Okay? Make sense to you? Okay. I'll make a remark. Okay. May work logically, but may be hard to help the proofs. Okay, the inference rule. Okay. All right, very good. So guys, why don't we take a short break, take attendance, and then we'll continue. All right? You guys may want to take a short break. Yeah, have your device ready, and then we'll do it now. Okay. 3342, yes. Okay, you can check in now, please. Good. Yeah, we're now taking attendance. Please get your device and check in. If you got any issue, I do have the sign-up sheet over here, which you can sign. All right, everybody's good? Okay, attendance. All right, everybody's good? Taking attendance? Yes. Yeah, your programming test one is going to be just the same value. I think that's on your guide too, the test guide, yeah.
So when I joined, it didn't first show like this page, so I left and joined again, and then I gave my answer. Is that fine?
Should be okay, but why not be, to be safe, why don't you sign anyway? So just in case, yeah. You want to bring your pen? And then, yeah, sign. Ryan, trouble?
Quick question. The attendance, but I just forgot.
It should be just by attendance, but why don't you sign just in case? Yeah, okay, good. Sarah? Yes.
I think over the weekend about office hours. Can I come a bit earlier today?
Yes, how early do you want to come? Maybe,
Whatever is good for you.
how about 3 p.m.? Would that work?
Yeah, yeah.
Why don't you come 3 p.m.? In case my door is shut, just knock. And then,
And I also have a question. Like, it says my attendance 100, but then it says like I missed some, but I answered it.
I don't know. Somehow, sometimes it does record attendance, but not for the poll. I think it should be fine.
Because I was there for these days.
Yeah, it should be okay. Just by attendance, that should be fine.
Okay,
Yeah.
okay.
All right. Yes. Question.
But the programming test,
Uh-huh.
would you be asking us like this? Or the way you did in lab 2, like you wrote like a whole story and we're supposed to translate that?
I think it might be a mix of both, but I'll make it kind of straightforward for you. I might just describe what the general problem is, and then pretty much like the first sentence over here, right? You can see here, I just talk about, in this test, you are required to build some model for this. Maybe very brief. I don't want you to read some very long paragraph.
Yeah.
Excuse me. You will read that first, and then I may or may not give you some requirement document summary, may not be necessary, but you'll definitely see something very similar to this. I would say, okay, now for this axiom, for this variable, you want to do this.
So
And
it'll
then
be step by step.
step by step, yeah.
Okay.
But sometimes it may not be to say, oh, now do some for all expression, may not be that, right?
Okay.
You have to,
So
yeah.
it'll be a mixture of both, basically.
Yeah, a little bit mix, yeah.
Most likely this way.
Most likely this way, more likely. Good, good, good. All right, guys, we'll start in about 1 minute. All right, just get ready. All right, we'll start in just 1 moment. All right, let's get started again. Okay. Yeah, before the break, we tried to go over with you about the abstract states, the concrete state or the refined state space. We got static part, dynamic part, and also variables and invariants, right? And let's now talk about once we get a state, the state wouldn't just stay constant. That's why they're called variables. So how can the state variable change? You'll be by occurrences of the events, like MLR, MLN. But now we got two new events to consider as well. Let's talk about it. Right, so this is something you have already seen. So the system is going to behave like an abstract state machine, like a transition diagram, which I drew earlier. It's going to evolve as the actions of the enable events. This is really important to know. Only the enable events can really occur and take this action into effects and modify the state variables. And if you went through, if you go through For example, the lab 2 solution walkthrough, I also try to draw some state diagram to show to you. Once you got the celebrity model understood, how can you visualize the execution of the algorithm? There will be some interleaving of the remove 1 and remove 2 events. That's something you can maybe also look into. That'll be beneficial not just for the programming test 1, but also for the exam as well. Right? Of course, you got to make sure the invariance is established and also always maintained after the state transition. Right? So here we got, we consider all events already existing in the M0, ML out, ML in. So these are the 2 old events. And we're going to talk about, at the same time, these events should be somehow overridden. I'm just using the Java terminology because now we got different variables to really look after to make sure they update properly. So we have to update ML out and ML in. That's what we have to do. Okay, so let's talk about ML out, ML in first. We'll talk about IL in, IL out a little bit later. Okay, ML out. This one here, the action is pretty straightforward. Think about what's happening over here. If you look at the diagram over here, right, just cleaner. So here we talk about ML out. Okay. And again, this will be the definition for ML out. A car exit from the mainland whenever this event occurs. So that means if you look at this diagram over here, that means there's a car over here that wants to exit from the mainland onto the bridge, if it is allowed to do so. In that case, it's going to be represented by ML out. In that way, which quantity should we update? It should be quite obvious, right? If you actually got, for example, here, ML out, it should only impact the reading of the server, the sensor that's actually put over here. In that case, we should really increment A only, whereas B and C should stay the same. All right? So that's why you see A should be the only one that will change. And one thing to note, in the initial model, there's only one state variable, N. But now we got more than one. So you have to really understand what this before-after predicate really is. Let me talk about it right away. When you look at ML out over here, this is the action, which contains only one. So this is a single action. But to be more precise about the effects, it really means you only list the action that's going to modify the value of the states. In this case, we're going to increment A to let A becomes its pre-state plus 1. Right? So the corresponding before-after predicate should be A prime equals A plus 1. That's the part you have to know. That's the only part that will change. We only modify the reading or the record of this quantity only. Whereas all the other variables which are not mentioned here should remain the same. How do we express that? Well, if B remains the same, that means B in the pre-state should be the same as B in the post-states, right? B prime should be equal to just B. C prime should be equal to C. And you want to make sure every one of them is true, right? That's a before-after predicate. Pretty straightforward, but you want to make sure you know that, okay? So for the action, you only specify what should really change. Whatever that's implicit, not covered over here, it's understood by the prover or by our generation process. They should remain the same. This is also very important to remember. When we generate a proof obligation, maybe next week, we'll have to use this insight as well. Okay? And symmetrically, if we have an occurrence of MLN, what does it really mean in the refined model? Again, the meaning doesn't really change from the earlier model. A car enters into the mainland. Okay? So that really means, let's see here. If I have a car that's really entered into the mainland, only this part over here, right? That's going to be represented by ML in. What quantity is going to change? Only C. It wouldn't impact anything about A. A should remain 0, by the way, right? Informally speaking. And also B wouldn't really change. B would have been changed already when that particular car tried to exit from the island. Would have been done that already. But now, when the car actually travels through the bridge and the cars try to go back to the mainland, that'll be represented by another event, MLN. Right? That's something we'll see later when we put all the 4 events together. Okay, so for this one here, similarly, right, you can see is decrementing C minus 1. And the before-after predicate, very simple, C prime equals C minus 1, and what's really implicit? A and B, so they don't really change, right? A prime equals A, and B prime equals B. Okay, that's before-after predicate. Let's get that part straight first. So this is to say, if the event is enabled, then this is some updates we can expect to happen if the event occurs. But what about the enabling condition for the event? That's the important part. The action part tells you how the variable should be changed. But remember, it cannot be unconditional, right? That's what our initial design for the initial model was, right? We simply put true and true over here. But somehow it will lead to invariant violation. We just cannot preserve the invariance. So now we should think about what these should be. And our consideration should be the guards should be designed in such a way that all the invariants we got over here should be somehow maintained. Should be. Okay? Otherwise, you will run into some unprovable sequence later. Right? Either way. All right, so let's now try to take a look. And to really save you some time, right? Of course, it's more like a trial and error process in case you really got the guards, let's say, wrong. In that case, you definitely got some proof obligation either on Rodin or on the paper that's unprovable. In which case, you have to review the unprovable sequence like how we did it last time and fix the model accordingly. That's one way. Or I can simply tell you that this is what you should do. Let's save some time. Let's do the second way. Okay? Yes? Yeah, that's okay. I want to give everybody, a chance. That's okay. All right, let's talk about ML out over here. For ML out, it turns out we need to have 2 guards. All right? The first one over here, we want to make sure in order for you to do ML out, thinking this way intuitively, ML out is actually going to be this way. So we want to make sure if a car is is allowed to really go onto the bridge, we want to make sure the current flow of the traffic on the bridge should be this way, but not the other way, right? Intuitively. How did we formulate that first guard? Edna, go ahead. Yeah, absolutely. Yeah, that was straightforward, but you just want to make sure you will be able to come up with that, right? So I think that this way, intuitively, it really makes sense. You want to make sure if you want to go this way, you want to make sure the other way has no flow. All right? Very good. Yeah, if I want to go this way, I want to make sure this way has no flow. Very good. So that means C equals 0 is one of them. Question? Yeah, we'll get to the NI guard, don't worry. It's not done yet. Okay, yeah. All right, so second one. Yeah, go ahead. Why don't I give everybody some hints and then you can go from there. Okay, why don't we do that? Okay. Oh, you also got some answer, right? Hold that. Okay. I know you guys are keen to try. Okay, the second one here. The number of cars on the bridge or on the island somehow limited. What does that mean? Okay. Basically, you want to think about if, let's say for ML out over here, I'm trying to add a card into here, right? But how is that limited? Okay, let me say this. I need to write down all the relevant constraints over here. So this one is a bit tricky, okay? And I want you to review something very quickly together. If you recall the abstract model, okay? in the concrete model, we talk about A plus B plus C should be equal to N, which is over here. There is some constraint about how large N could be, which is over here, right? This constraint over here is not explicit when we define M1, but you have to keep that in mind. Because later on, when we put the proof obligation for each one of them, for invariant preservation, invariant establishment, we have to put the abstract model's constraint also into the hypothesis. That's what we have to do. Okay, let me say that again. We want to design, oh, sorry, you already saw the answer, right? My bad, I should have hide that. Okay, maybe you didn't see that. Anyway, so let's explain a little bit why this is the case, okay? I'll derive that together with you, okay, before I get there. You want to consider, number one, this is the linking invariant, linking A plus B plus C and also N, the concrete and the abstract, number one. Number two, we know that the abstract variable actually got some maximum, should be less than or equal to D, which denotes the maximum number of cars that can be on the island and the bridge, right? Considering this and also this, we can derive this particular guard. But how? Let's take a quick look, right? Okay, let's now write down what we know. From M0, we have N less than or equal to D. Okay? And then we also got from M1, we actually got A plus B plus C equals N. Right? Over here. So that means right now, if I want to increment A such that A becomes A plus 1, right? So that means A over here is not going to be A. It's going to be the pre-state value A plus 1. And how can I be sure? If I add this A plus 1 plus B plus C together, the resulting N is going to be still less than or equal to D. That's the issue we're having. Okay? Let me annotate a little bit further. This N over, so once I get A plus 1, so this is the effects of ML out. And B and C, they don't really change. And M over here is really M prime. I want to make sure in the post states, the constraint from the initial model will still be satisfied. That means I want to have M prime less than or equal to 0. Right? Let's now look at these two predicates. And the resulting guard should be quite obvious. We have, number one, M prime should be less than or equal to D. And A plus 1 plus B plus C should be equal to M prime. Okay, let's do some substitution. Think about steps. Step number 1, step number 2, and step number 3. Let me put it here. Let's replace M prime by this guy over here. Okay, so M prime will just be A plus 1 plus B plus C, right? And then should be less than or equal to D. Okay, and a little bit more. Based on the first guard, we know that C is equal to 0, right? So we don't need to consider C over here, all right? Are you guys following so far, right? It's not too bad. Okay. And we know that C is also 0 because of the first guard. Okay, let's simplify that. So that means A plus 1 plus B less than or equal to D. We are getting very close. Okay, let's do a little bit more. Yeah, I'll try to recap after this. That means A plus B less than or equal to D minus 1. And we can get rid of D, minus 1 by rewriting it to be A plus B strictly less than D. That's what you have. Okay. let me put it down. A plus B strictly less than D. Let me reiterate about the point once more. Okay. The way to figure out this guard, either you go by thinking ahead about what the state change is going to happen and try to see what's going to be the impacted invariance in both the abstract and concrete states and figure that out accordingly. That's one way, which is what we did. Another way is if you don't really have this guard for now, what's going to happen is you're going to reach to some unprovable sequence when you try to prove when you try to discharge the invariant preservation proof obligation. In that case, you will still come back to add this guard anyway, either way, okay? Now, how do we go for the first way? The relevant invariant we should really consider, again, you want to go back to the comparison between initial and also first refinement. We now want to figure out the guard for ML out, which modifies A. Okay? So this is one invariance that's really important. You want to make sure A plus B plus C remains to be N. And then N itself in the abstract model is constrained to be no more than D. So these are the two constraints we want to make sure that will be satisfied. And we make sure this will only be maintained when the event should only be enabled when we can be sure these two invariants can be maintained. Okay, let's go back. Okay, once more. So number one, think about this think about the constraint in the abstract model. Number two, think about A plus B plus C equals N in the concrete model here. And now we know the effect will be A becomes A plus 1. So that's why we replace A over here by A plus 1, right? And then the resulting value is going to be M prime in the post states. And M prime in the post state should be subject to that constraint we spoke about in the initial model, right? So that's what we have. And then to some simplification, that's what you have. Okay? So really important for you to not just memorize the guard. That's not the point. You should really ought to understand how we derive it. Okay? Question? Okay, think about it this way. So ML out, before we have the pre-state and the post-state, right? It's actually right before you try to take the action. That'll be the pre-states. And right after you take the action, it will be the post-states. So right after you take the action for the ML out, A is going to be incremented by 1. So that's why I will just replace the A, the pre-state value, just by A plus 1, because you'll be incremented by its pre-state value plus 1. And once we do this addition together, the resulting N should not be the pre-state value N anymore. That should be the N prime. Yes. Uh-huh. Mm-hmm. No, nothing wrong. Actually, I think in this case, I think either leaving that this way unsimplified, it could make maybe the proof a little bit find it a little bit more difficult. You want to make it as compact as possible. That's why we try to do simplification. Mm-hmm. Yeah. Yeah. Yes. Oh, sure, sure. So basically, you're saying, let me see this. Mm-hmm. Yeah, you mean this one here, right? Okay, no problem. So I'll give you one example, right? So let's say, I can even do, if x less than or equal to y minus 1. Think about, let's not even worry about a and b, just x. That's really equivalent to x is strictly less than y. That's a general form, okay? So think about, let's say if, a little bit like this. Let's say x is over here, and y is over here, okay? If I say y minus 1 is somehow the upper bound for x, that means y itself must be strictly larger than x. On the other hand, if you put x and y to be just equal to each other, it's not going to work. Because in that way, y minus 1 is going to be over here, which cannot be the upper bound for x. Right? Just try to draw some diagram and then maybe to visualize it. Yeah. Mm-hmm. Okay? Yeah. Of course, guys, if you feel a little bit uncomfortable about this kind of rewriting, it'll be quite important for the bridge controller since we're only dealing with numbers. Think about it and then reach out if you need some help. All right. Let's now, okay, I would say this might be the most tricky for today, right? You kind of got it through, okay? And the next one. All right, so we already got, so what about MLN? MLN, we only got one guard, right? So MLN is going to be, we want to make sure there's some car on the bridge heading to the mainland. What does it really mean? Basically, for this one here, we want to make sure MLN is going to make this move. In order to do that, we have to decrement C over here. And the only thing we have to make sure is C is got to be larger than 0. Otherwise, you will decrement from 0 to -1, right? It's got to be positive. And I have a challenge for you. I'll write it down first. C larger than 0. That means there's at least one car that's on the bridge heading this direction here, so that car may just go back to the mainland. That's what the MLN can do. Question for you. Is it necessary to add a guard? You might be thinking, if I'm moving this way here, that means this way here must be 0. Should we also say A is equal to 0? First of all, I agree, A equals 0 should be true. But is it really necessary for us to put it here? Go ahead. Daba. Sorry, say it again. ILL. That one there, yes, in some way, yeah, you're right, yes. But any other insights? That's quite true. Yes, go ahead. Aha. Okay, very good. I think another what you just said is also very true. Okay, but what you said was a little bit look ahead. So the actual events that's actually going to check that A is equal to 0. Okay, is going to be the events for IL out over here. So, but we'll talk about this event later. So that's a look ahead you guys can keep in mind. But I think the more relevant answer would be the reason that we don't need this one because we already got invariant number 5. Given this, and we know that C is larger than 0, that means this part is false. Then it's got to be that this is true. Okay? All right, so the answer is no. Because given that C larger than 0 and this particular invariance, which is A equals 0 or C equals 0, the whole thing, sorry, I'm running out of space, that implies A equals 0. That one's implied automatically, logically, so we don't need to. But if you by adding it, you can help the prover, you should really do it. But for now, we don't need to. Okay, Sarah. That's okay, nothing wrong with it. That might help the prover, sometimes it may not. So I would say it depends. In case this is on a programming test, then if you believe that one's going to help the prover to do the proof, you should add it. That's on the paper, you should really only add things that's really required. Yeah. Okay. All right, so guys, I would say this question here is even more important than the guard itself. Okay, just make sure you understand that. Okay. Okay, very good. I think I want to have one more discussion very quickly, and then we can talk about your practice test one solution very quickly. Yeah, go ahead. The question was, how do I know the guards I have so far is just enough? It's a very good question. I don't know in general. Because, again, the standard answer should be, go with what you believe should be enough and stay with that. And then generate all the proof obligation as sequence and try to prove each one of them. If you're able to prove all the sequence, that means those guards being part of the hypothesis will be enough. On the other hand, if you got any unprovable sequence for any of the proof obligation, in that case, there's something wrong with your model. And not having sufficient guard could be one reason. That'll be the general answer. Yep, yep. Well, of course, it depends on how I might ask the questions. Let's say if I say, okay, now try to design the events so that you have sufficient guard. If I don't give you any extra hints, in that case, yes, you may have to come up with something and then try to justify them, right? On the other hand, sometimes I might say, okay, for part A, I want you to have this particular guard. This is how we can describe it in English and formulate it in math. That might be more likely to be the case in the exam. Yeah. Well, I might say, consider the current list of guards over here for this event, but something missing. What is that? In that case, you may have to prove some proof obligation and then try to find out what's unprovable and fix that accordingly. Yeah. Okay. Yeah, let me spend only about 5 minutes, and then I want to summarize about what we got so far, and then we'll continue from next Tuesday. And then I can speak briefly about a practice test 1 solution. Okay, so let's now go back to the slides quickly. Right, before, after predicates, I'll talk about this maybe next time, but let me just go to the slide that will summarize. Okay, this one here, very quickly. Okay, so this part over here really try to compare to us about the 2 states, right? So you got shared static part. So that's a constant and axiom. It is shared by initial model and also the concrete model over here. And then we got over here, these 2 are the old abstract events. Old abstract events. And these 2 over here, they are the new concrete events. Oh, sorry. They're the concrete events. How about, let me, just for now, I'm going to talk about new next time. They are more the refined events. Basically, these old events already exist in the initial model, but now we're trying to refine them or try to override them with different actions. Okay? And it is important to really see, for example, over here, the action over here is trying to modify the concrete states. And over here, the action over here is trying to modify the abstract states. The abstract states. And what about the invariants? If you look at this very special one over here, so this one over here is, how about this? Let me put it this way. All the invariants over here, every one of them, is called the concrete invariants because they involve at least one concrete variable. A here, B here, C here, A, B, C, A, and C, right? They're called concrete invariants. Involving one concrete variable. And the one that's really special is this one here. And this is what we call a linking invariance, which is also a concrete invariant, of course, which involves both the abstract and concrete variables. You can see this one here is actually abstract variable, right? Just to clarify terminology. And a little bit look ahead. What we have to do next Tuesday. This is the abstract guard. This is so-called a concrete guard. They should be related in a specific way by logic. That's something we'll talk about next time, okay? And I'll make notes, and then we can move on to talk briefly about your practice test 1 solution, okay? The abstract guard and the concrete guard should be related logically, but we'll get there next time. All right, any question? All right, this page, nothing new, just summarize, okay? All right, so got about 5 minutes or so. Let's see what we can do, right? I already got a solution here, and let's have a very, very brief walkthrough. cannot do too much right now, only got 5 minutes, but if you got a follow-up question, let me know. I still have office hour today and tomorrow, okay? So let's see anything interesting here. So we got carrier sets. Make sure you can do carrier set. Let's say student and the course, okay? And we got two constants, like a cap and limits. I would say these two limits are like a credit limits, like a C, back in lab number 1, right? Don't forget about, we don't cover just lab 2, but also lab 1, right? So these are like a credit limits in your lab number 1. And 1, is it natural number? Starting with, no, they're not, they're more like a special, like a proper subset of natural number, right? Positive number, okay? So we got cap and we got limits, okay? And some of you, when you ask me a question during my office hour, you already use this for your lab number 2. So the finite is a special query you can check whether or not the student is finite set, okay? So this turns out to be necessary when we try to prove something about the cardinality. But I would say if you're required to write these two, right, I will tell you explicitly in the programming test 1, just to save time. But just remember you got these two facility over here for you. In case you want to prove anything about the cardinality of the set, because it should be some finite number for you to manipulate. So that means these two sets should be finite. Okay. All right, let's take a look over here. Right? Well, looks pretty much like a math review lecture, right? So guys, what is this? Partial function. I like it. Very good. Okay, not just function, partial function. Having a okay, let me do a little bit. I will do as much as I can. Really important for you to recall. When I say C is a partial function, right? That means I don't require every student to have enrolled already in a course. I don't require that. There might be some students who haven't, there are simply some students who do not exist in the enrollment system. Okay, I'll write it down. So the partial function over here is really important for you to note. Okay, partial function. That means not all students exist in the enrollment system. Okay, that's why it's a partial function. Otherwise, it would be a total, but it's not the case. And are you comfortable with this universal quantification here? Isn't that similar to say every account in the bank should be larger than or equal to minus C, right? Similar, right? Let's take a look. We say for every A, well, it should be for every maybe S for students. Somehow TA, forgot to rename, but that's okay. Dummy variable name doesn't really matter. Let's say for every A, the student must be in the domain of the C, which is this function. Because we want to do function application, you have to make sure in order for the function application to be well-defined, right? We'll talk about well-definedness in lab number 1. In order for function application to be well-defined, the value here must be in the domain, okay? Let me highlight that. This guy here is to make sure this function application over here is well-defined. Okay? Well-defined. And then we're saying the number of courses, the number of enrolled courses for all the students in the enrollment system should be less than or equal to the cap. Write that, right? And the final one, you can see the cardinality of the C function. That means how many students are there in the enrollment system. That will be subject to the limits of the school, how large the school can be, right? Okay, other than that, I think initialization would just say initially just empty school to begin with. It's a very very reasonable initial value for any function. Right, let me see. Okay, so do you know what the symbol is? Overriding? Okay, you might need that. Very likely. I'm not saying you will need that. You might need that. Okay, make sure you know how to do that. And then, how about this one? Subtraction? What kind of subtraction? Domain or range? Domain, because it's on this side here, right? Okay, don't abandon what you learned, in the math lecture, right? And over here, and okay, I see. Okay, again, it's overriding, and you may have, there's a single pair. So that means we're going to update just for this particular student, which is the input. And it should really map to this particular, whatever course before and this new course, all right? And then, so this is the symmetric operation. We want to remove its courses, all right? All right, guys, it was a very quick walkthrough. I'm running over time. Thank you so much. And then if you got any question, let me know. Still got office hour today, tomorrow. And I'll see you on Thursday, Williams Small Center. All right, take care. Bye-bye.